Hello everyone, my name is Rocco Tedesco, but most of my peers know me as Rocco. And for my ARP project, I will be looking into building a better drivetrain for first high school robotics. So my question is, how can the Andymark kit of parts, or KoP, AM14U4 drive chassis be refined so that it's more competitive and versatile while also retaining its affordability? As you can see on the right, I have a picture of a 3D rendered version of the drivetrain in question. Um, this drivetrain, probably the most famous drivetrain amongst the high school robotics community, um, for a lot of reasons. Some of them being, one, it's a very simple drivetrain. It's very easy to build. Um, Two, it's accessible. When rookie teams register for their first competition through First, oftentimes First will have deals. They will give the team the kit of parts drive chassis for free. This ends up saving the team roughly $500 that they can then put towards other parts or even more competitions. Um, that's part of the reason why it's so popular amongst young and inexperienced teams. Additionally, there's just so many resources to help them build it. The problem with it, though, is that it can be limiting. Um, there's a lot of drawbacks to this drivetrain. And to figure out a lot of these, I took my research to Reddit. I put a post out asking if just simply what their thoughts were and what could be improved. And the feedback I got back uh, came in forms of them asking for more wheel options or flexible gear ratios. They also complained about the lack of flexibility with the pre-drilled mounting holes, as having to stick with these can often limit how you design the rest of your robot. Additionally, the dimensions are restrictive. They only have really two options as to how you can configure your chassis. And as you can see in this picture, you can either do a long bot or a wide bot. So how can this drivetrain be improved? Well, for one, just looking at the pros and cons, like I said, it's simple, very easy to build, a lot of resources to help. Additionally, it's very robust. This drivetrain can take quite a beating and will still hold up throughout the season. On the other hand, there's a lot of complaints of it being underpowered. They can't send enough power to the gearboxes using the required motors. Like I said earlier, you can't change the gear ratios. And additionally, it's only a single speed gearbox, meaning you're stuck with whatever gear ratio is already in there, and you don't have the ability to change gear ratios on the fly in the middle of a competition. So how can I improve the gearbox? Well, for one, I could use a different variety of motors. You can see here are just 6 of the available motors, but there's so many more, and I can use really any combination of these, or even just multiples of some of them. Um, I can make it pneumatic gear shifting compatible. Uh, so, like you see in these designs of gearboxes, I can make it so that there's 2 stages of gearing, and you could switch between them with a press of a button, which would trigger a pneumatic piston, furthermore changing the gear ratio. Um, I could incorporate room for a third motor, whereas the original gearbox only accommodates 2. And then I can find the perfect gear ratio using software like what you see here, which is called the JVN Design Calculator, which I'll get more into later on. Before we continue any further, I must give you all a disclaimer. Unfortunately, due to the circumstances that we're living in today, COVID-19, I was unable to have access to the resources I needed to be able to carry this project fully out. Um, Despite having design plans and tests planned out and all the necessary further steps, COVID has prevented me from being able to carry this out, and therefore the remainder of this presentation is an explanation of what I would have done and what I would have expected to come out. Um, so I hope you all can still get something meaningful out of the rest of this presentation and maybe still learn something. But it breaks my heart that this wasn't able to be fully carried out. So moving on, the test. For one, this would start with me designing and building the product. Like I said earlier, I would use computer animated design software, otherwise known as CAD, like the one you see above, SolidWorks. And I would also use software like the JVN calculator, which is a calculator designed in a spreadsheet, which enables the user to put in the desired amount of motors and what kind of gear ratio they want, and the calculator will output theoretical numbers that represent what the user can expect to see from the product of what he's designing. From there, I would move on to building it. I would work in a workshop like the one that you see here, and I would put together the gearbox with my own hands. I had plans to probably 3D print the housing of the gearbox and then use machine shopped parts to construct the rest of it. After the gearbox is built, I would have to build the chassis like the one that you see on the table, and I would have to build two of them, one for the newly redesigned gearbox and one for the control, or the gearbox that I'm trying to redesign and make better. After everything's built, I would move on to testing, and I would put each chassis, both the product and the control, through a series of the same trials and tests. And these would range anything from speed tests to acceleration to turn radius, to pushing power, see how they do on defense. After I have all the data I need, it would be time to analyze it. And when I'm doing this, I'm going to first look at the numbers. The numbers don't lie. I can take each data sheet from each trial and simply trial by trial comparing the numbers from each result, and that alone will tell me how well each component performed compared to its control. But on the other hand, because there's so many variables that are to be looked at, it's important to view this data holistically. It's a very high possibility that some numbers will show improvement while others will either decline or stay the same. And so by viewing this holistically, I would have to make the decision if a great increase in one area is worth the decline or stagnant of another area. And that would all inform my decision on whether or not my product is better than the control. Now, if this project were to be taken all the way into something that would be able to produce a product that could be sold at retail or be used professionally, further testing would probably need to be conducted. I would want to look into consumer testing and having trusted consumers try out my product and give me their reviews. They could use it on their own robots with varying designs, and I would use their feedback as analysis. But whether or not I use consumer testing, that final analysis would have to tell me whether or not I need to go back to the drawing board and resume the engineering process as I've identified on the right. And this would entail looking at my final product and identifying the issues within that one instead of the control as we had originally done, And then from there, I would go as I had originally done, and I would design and build a solution. I would test the solution and then reanalyze. Thank you for listening to my presentation, and I hope you could get something meaningful out of it.